It's late. You're sitting at your desk, you drop a massive, completely broken block of code into your terminal, you send it off to an API,
Mhm.
and like 3 seconds later, it comes back completely fixed.
Oh, yeah, best feeling in the world.
Right. It feels like magic. It feels like the machine just sat there, read your logic, and, actually thought through your exact problem.
Mhm.
But what if I told you the system on the other end didn't actually understand a single line of that code?
Huh.
What if, despite all appearances, you are basically just interacting with the world's most sophisticated multi-billion parameter game of autocomplete?
I mean, that is the defining technical question right now, period.
Yeah.
Even the engineers, like the ones training these foundational models at the deepest levels, they're looking at the outputs and struggling to give a definitive answer about what is actually happening under the hood.
So that's what we're getting into today. We're opening up a whole stack of notes on the single most hotly debated question in AI right now.
The great debate.
Exactly, the great debate. Can large language models actually reason? Because from the outside looking in, it really feels like we're trying to figure out if the person on the other end of the phone is uh, a chess grandmaster
Right.
or just someone reading really, really fast from a remarkably thick rule book.
That's a perfect analogy. And the tension in all of our source material revolves entirely around that unsettled conflict.
Yeah.
Are we witnessing genuine reasoning, or are we just seeing a high-dimensional pattern-matching engine that has basically learned how to convincingly mimic the shape of reasoning?
Mimic the shape. Yeah.
Right. And before we dive into the actual architecture of how these models operate, we have to look at why this debate is completely dominating the software engineering space right now.
Let's get into that because, a lot of people listening might assume this is just some uh, philosophical debate.
Oh, totally.
It sounds like something cognitive scientists argue about in a paper,
Right.
right? Not something that actually impacts a 2-week sprint cycle.
But it dictates reality for anyone building software right now. Like, this is far from a late-night dorm room debate about the nature of consciousness.
Right.
It has massive, immediate, practical implications for you as a developer. Whether an LLM is reasoning or just pattern matching changes the fundamental architecture of how you deploy these systems in production.
How so?
Well, it changes your risk model entirely. If you are building an application layer on top of an API, your whole strategy for error handling, sanitization, system trust, all of it depends entirely on understanding the mechanics of the engine you are querying.
Okay, wait, and I'm going to push back a little here.
Sure, go ahead.
From a purely pragmatic standpoint, do I actually
You
care?
should.
But say I am building a data extraction pipeline, right?
Yeah.
And I ask the API to parse a messy block of unstructured text into a specific schema. And the output comes back perfectly formatted as JSON, like 99% of the time.
Hmm.
Whether it reasoned its way there or just matched a really good statistical pattern, I mean, it feels like an academic distinction. Utility is utility, isn't it?
I get that.
If the output is flawless, the mechanism shouldn't really matter to the end user.
Well, okay, if the pattern matching were truly flawless in all contexts, then yeah, the distinction wouldn't matter at all. You could just treat it as a black box and walk away.
Right.
But here's the catch. Pattern matching has distinct structural boundaries. It has blind spots. And when a pattern matcher fails, it doesn't fail the way a reasoning human fails.
What do you mean? Like the types of errors?
Exactly. Think about it. A human engineer makes logical error, right? They miss a semicolon or they misunderstand a variable state.
Standard bugs.
Standard bugs. But an LLM fails in ways that are totally unpredictable, completely bizarre. And they're incredibly difficult to catch in a standard testing suite.
Because it's not a logic error.
Right. Because you, as a human, are unconsciously projecting human logic onto a system that doesn't actually possess it. You assume it understood the assignment, so you aren't even looking for the completely irrational hallucinations it might produce.
Wow. Okay, yeah. We really need to look at the track record to ground this, I think. Because looking at the research notes, the evidence for reasoning is, it's honestly staggering.
It really is.
You see these models doing things that, if a human developer did them, we would instantly classify it as high-level cognitive work.
Oh, absolutely. They exhibit behaviors that map perfectly onto our definitions of deep analytical thought.
Yeah, and the sources actually highlight 4 major capabilities that make this case.
Let's hear them.
First is novel problem solving. We are seeing models tackle edge cases, bizarre architectural prompts, and logic puzzles that they have definitively never explicitly seen in their training data.
Right. They aren't just, regurgitating a Stack Overflow thread.
Exactly. They are synthesizing a novel solution on the fly, which feels Very much like reasoning.
It does. And then you have cross-domain transfer, which is maybe even more compelling.
Oh, great.
This is the ability to take rules or structures from one completely distinct area and apply them to an entirely different one.
Give me an example.
So, for instance, a model can absorb the underlying logic of a specific, highly optimized sorting algorithm in Python, right?
Okay.
And then spontaneously apply those abstract organizational principles to restructure a massive, messy legal document.
Oh, wow. That's wild. Okay, so that's two. And third is step-by-step decomposition.
Right.
You ask an LLM to design a full-stack web app, and it doesn't just vomit code all over your screen.
Hopefully not.
Right. It actually breaks the project down. It establishes the database schema first, then it moves to back-end routing, then handles front-end state management. It maps a logical journey from A to B.
Which is exactly how a senior engineer would approach it.
Exactly. And fourth, and this is the one that really, really blurs the line for me, self-correction.
Oh, yeah. This one is spooky.
You can point out a flaw in its logic, or sometimes it even catches its own error mid-generation. It literally stops and outputs something like, wait, that loop condition will cause an index out of bounds. Let me refactor that function.
Right. So when you string those four capabilities together, novel problem solving, cross-domain transfer, decomposition, and self-correction, it paints a really vivid picture of a cognitive engine at work.
Yeah, it screens reasoning.
It does. But, and this is a big but, this brings us to the counter-evidence. Because the entire argument against true reasoning hinges on a massive structural vulnerability in how these models behave.
Right, the Achilles heel.
Exactly.
Yeah.
They exhibit an extreme, almost comical sensitivity to entirely irrelevant details.
Okay, yes. This is the blue train problem from the notes.
Yeah. Yes, perfect example.
This completely flips your perspective on the intelligence of the system. Like reading this, it's like having a brilliant engineering student who can write a super complex machine learning algorithm flawlessly, right? But if you add a single comment to the top of the file saying, and the server rack is painted blue, they suddenly forget how to write a basic array.
Exactly.
A reasoning entity ignores the paint color because it understands that color has zero mechanical relationship to the code. A pattern matcher gets entirely derailed by it.
Right. And to understand why that happens, you have to look at the underlying architecture, specifically the attention mechanism in transformers.
Okay, let's break that down.
So when a human reads the phrase blue train in a math problem about velocity, our brain assigns zero weight to the word blue.
Because it doesn't matter for the math.
Exactly. We possess an abstract mental model of physics, and color doesn't factor into the equation. But in a transformer model, there is no abstract mental model.
Right, it's just math.
Just math. The attention heads are mathematically mapping the relationships between all the words in the prompt simultaneously.
So the model is practically forced to process the color.
It doesn't just process it. The introduction of the word blue generates actual mathematical vectors that interact with every other token in that prompt.
Oh, I see.
It pulls the model's attention away from the core variables. It forces the system to traverse a different latent statistical space entirely.
So I was wandering off.
Yeah, suddenly the probability weights of the next token shift, dragging the output down this massive rabbit hole of irrelevance. The model wasn't holding the abstract concept of velocity in its mind. It was just navigating a high-dimensional web of word associations.
Wow.
Introduce a new, completely irrelevant association, and the illusion of reasoning just shatters completely.
But wait, that fragility introduces a massive paradox.
It does.
How can the exact same neural network take a complex sorting algorithm and reorganize a messy legal document flawlessly to completely break if you add an irrelevant adjective to a high school math problem?
That's the million-dollar question.
What is structurally happening inside the model that allows both superhuman brilliance and, frankly, sheer stupidity to exist at the exact same time?
So the sort material actually introduces a psychological framework to make sense of this exact contradiction. It maps the behavior of LLMs onto the human concepts of System 1 versus System 2 thinking.
Okay, yeah. System 1 being our intuitive, instinctual brain.
Yes. System 1 is fast, it's automatic, associative. It's the part of your brain that instantly knows the answer to 2 plus 2, or catches a falling glass before you even realize it slipped.
Or reading someone's expression.
Exactly, reading the emotion on a coworker's face in a fraction of a second. It is rapid, subconscious pattern recognition.
While System 2 is the slow, deliberate, analytical engine.
Right.
It's what kicks in when you are asked to multiply, 417 by 83. You can't just intuit the answer.
No, unless you're savant.
Right, you have to stop, allocate mental energy, hold information in your working memory, apply a sequential set of rules, and logically arrive at a conclusion.
Exactly. And applying this to the architecture of an LLM is really where the paradox resolves itself. The consensus in the research notes is that large language models are wildly, almost incomprehensibly powerful System 1 thinkers.
Oh.
They have absorbed the statistical relationships of the entire digitized internet. Their instincts, so to speak, are incredibly vast, but they completely lack genuine System 2 capabilities.
Because generating the next token is just a fixed compute operation.
Precisely. In a standard forward pass, the model spends the exact same amount of compute to predict the next word in a nursery rhyme as it does to predict the next step in a complex mathematical proof.
It can't try harder.
Right. It physically cannot pause to allocate more compute or deeper analysis to a harder problem. It does not possess an underlying, slower analytical engine to step back and double-check the logic of the intuition it just generated.
Wow.
It is operating entirely on highly advanced instinct.
So think of the model like a master jazz musician who has never actually learned how to read sheet music or study music theory, but has somehow listened to every single recorded song in human history.
Oh, I like that.
If you start playing a melody, they can instantly harmonize with you flawlessly. They look like a total musical genius. But if you stop and ask them why they played a C sharp in that specific chord progression, they can't tell you.
Nope.
They don't know the rules of harmony. They just knew statistically, instinctively, that the note belonged there.
That is the perfect mechanistic analogy. The model doesn't know why the code it generated works. It just knows that tokens in this specific sequence have a highly probable association with the prompt you provided.
Which brings up a really critical question for the engineers listening right now.
Let's hear it.
When developers use prompting techniques like chain of thought prompting, where you explicitly write, take a deep breath and work through this step by step, are they basically trying to artificially duct tape a System 2 onto a System 1 brain?
It is absolute duct tape, yes. Because the model lacks an internal scratchpad to silently deliberate, you are forcing it to use its own external output as that scratchpad.
Oh, I see.
By forcing it to print the first step, that print step now becomes part of the context window for generating the next step. You are taking a massive associative System 1 engine and constraining it.
You're narrowing the focus.
Exactly. You are forcing the statistical probabilities into a tighter, more linear corridor to basically simulate a System 2 process.
But the core engine hasn't actually changed. It's still just instinct driving the bus, even if you are forcing that instinct to move 1 inch at a time.
Right. Which means it can still be derailed. If the pattern hits a dead end, or if an irrelevant detail like our blue train pulls the attention heads off course early in the chain of thought, the model will confidently hallucinate an entire logical sequence based on a flawed premise.
So if we accept this premise, that LLMs are operating as massive, disembodied System 1 brains without a true System 2, what exactly are we dealing with? Because we keep comparing it to human cognition, but it clearly isn't human.
The notes emphasize a very crucial nuance here. It is really easy to say, oh, it's just pattern matching and write it off as a parlor trick.
Sure.
But that minimizes the reality of what is actually happening at scale. When you scale up pattern matching to hundreds of billions of parameters, something reasoning-like genuinely emerges from the statistics.
And it's different.
Very. It is an alien form of intelligence. It operates with completely different properties than our own minds.
So it's a system with superhuman breadth, but subhuman filtering. Like, a human engineer cannot instantly synthesize a design pattern across 50,000 lines of legacy code in 3 seconds.
Impossible.
The model can. Its breadth of association is vastly superior to ours, but it is profoundly weaker in its physical common sense and its inability to ignore a blue train distraction that a human child would filter out instantly.
Exactly. It is a fundamentally new category of cognition. And because it is so alien, deploying it requires a very specific operational mindset. The source material outlines some highly actionable architectural advice for practitioners building on top of these models tomorrow morning.
Okay, let's translate those directives into concrete engineering practices for the audience. The first one is straightforward but vital. Do not dismiss the capabilities.
Right.
You can't just wave your hand, say it's not real reasoning, and refuse to integrate it. The economic and operational utility of this emergent behavior is undeniable. If you aren't using it for boilerplate generation, code review, or unstructured data parsing, you are operating at a massive deficit.
Spot on. But the second directive is the necessary counterweight. Do not blindly trust the output.
Never.
Because of that lack of intrinsic System 2 guardrails, the potential for silent, confident failure is literally always present. You have to design your system architecture assuming the LLM will occasionally lie to you with absolute syntactical perfection.
Which leads perfectly to the third and fourth directives, testing and independent verification. And this is where we have to move beyond generic advice.
Right. Test thoroughly isn't enough.
Yeah, it doesn't just mean running a few happy path prompts.
Sure.
You have to build stress tests that intentionally inject irrelevant variables into your prompts to see where the attention mechanism breaks down. You have to map the boundaries of the illusion.
And you must verify independently at the architectural level. Never let an LLM handle the final layer of your application state.
That's a great rule.
If the model generates code, pipe it through an abstract syntax tree parser or a deterministic compiler before it ever reaches execution.
Right.
If you are using it to extract data, do not trust its JSON output natively. Force it through a rigid schema validator, like Pydantic in Python, to enforce deterministic structure before your broader system ingests that data. You use rigid, non-AI systems to check the homework of the AI system.
So you essentially build a deterministic cage around the probabilistic engine.
Yes, beautifully put. You structure the workflow so its alien strengths are amplified and its unpredictable weaknesses are caught by traditional software engineering guardrails.
Makes sense.
And the final directive from the notes is to stay current with the rapidly evolving research, specifically around test time compute.
Oh, yeah.
The industry is aggressively trying to build native System 2 capabilities into these models, changing how they allocate compute during inference. The boundaries of what is just pattern matching are shifting every single month.
You know, natural language is inherently messy. It's subjective. You can easily fake reasoning with a really eloquent, well-structured paragraph that just sounds confident.
Totally.
But you cannot fake math. Mathematics is a rigid, unforgiving domain.
It is. Math strips away the linguistic flourishes. It mercilessly exposes the naked mechanics of the model.
And that is exactly where we're heading next, based on our source notes.
I can't wait for that.
We are going to take this entire debate out of the realm of code and poetry and into the realm of raw mathematics. We're going to explore how numbers expose the limits of pattern matching in ways that natural language easily conceals.
Because when you ask a statistical engine to perform rigid deterministic logic, the cracks in the System 1 architecture become incredibly visible.
Right. Before we close out this session, there is a lingering thought from the research that you should really mull over while you're staring at your terminal tonight.
It's a heavy one.
We've spent this entire time analyzing how AI simulates logic through raw statistical patterns, next word prediction, and high-dimensional vector spaces. But if an alien, reasoning-like behavior can genuinely emerge from nothing but raw probabilities and pattern recognition,
Right.
what does that imply about human reasoning? Is it possible that our own vaunted System 2, that internal, deliberate, analytical monologue we prize so highly, is just a biological version of highly advanced pattern matching?
It really forces you to question the mechanics of your own intuition, doesn't it?
It absolutely does. Something to think about the next time you're waiting for that API response to stream back. Keep questioning the patterns.